Ever wonder if AI is telling you the whole truth, especially depending on where you are in the world? Or how we can build AI assistants that actually do things, not just chat? We're diving deep into some fascinating research today that tackles these questions head-on.
Exactly. We've got a packed agenda. First, we're unpacking agentic LLMs. Think of them as AI with a to-do list, capable of reasoning, acting, and interacting. Then we're tackling a critical issue. How well do these models fact-check information across different regions of the globe? Prepare for some surprising disparities.
Next up, we're comparing different ways to analyze mental health text using AI, prompt engineering, RAG, and fine-tuning. We'll break down what those terms mean and which method gives you the best bang for your buck. After that, we're exploring how AI is revolutionizing materials science, specifically polymer discovery, using a cool technique called multimodal learning.
And finally, we're wrapping up with a look at code switching. That's when you mix languages in a sentence, and how it affects AI performance in tasks like translation and speech recognition. So buckle up, it's going to be a fascinating ride.
Okay, let's dive into this paper on agentic LLMs. It's a hot topic, and this seems like a good overview. The core idea is that we're moving beyond just language models that predict text. We're talking about LLMs that can reason, act, and interact.
Exactly, it's like giving these models a brain, hands, and a social life. The paper breaks down the research into those three key areas: reasoning, acting, and interacting. Makes sense, right?
Totally. So reasoning is all about improving decision-making. Think reflection, retrieval of information, and better problem solving. They mention chain of thought prompting. What's that about?
Chain of thought. That's where you prompt the LLM to break down a problem into smaller, logical steps. Instead of just asking for the answer, you guide it to think through the process. It's like showing your work in math class.
Got it. And that helps with accuracy, I assume, because I know LLMs can sometimes hallucinate, make stuff up.
Big time. Hallucination is a major issue. Chain of thought can reduce it by forcing the model to be more grounded in logic. They also talk about self-reflection, where the LLM evaluates its own answers and tries to improve them. It's like AI debugging itself.
That's wild. So what about acting? What does it mean for an LLM to act?
Acting is where things get physical, or at least more practical. It's about LLMs using tools and interacting with the real world. Think robots, APIs, and assistants that can perform tasks for you. They mention world models. What are those?
I think that's where the LLM has some kind of internal representation of the environment it's operating in. So it's not just blindly executing commands, it has a sense of the consequences of its actions.
Precisely. And that's crucial for things like robotics. You need the LLM to understand that if it tries to move a cup through a wall, it's going to fail. They also bring up Vision Language Action Models, or VLAs. Those are super cool.
VLAs?
Okay, imagine an LLM that can see the world through a camera, understand instructions in natural language, and then act by controlling a robot. So you could tell it, pick up the red block and put it on the table, and it would actually do it.
Whoa, that's a huge step up from just generating text. So what about the interacting part? Is that just chatbots?
It's more than that. It's about LLMs understanding social dynamics, playing roles, and even simulating entire societies. They talk about theory of mind, the ability to understand that other agents have their own beliefs and goals.
Like knowing that if I lie to you, you'll believe something that isn't true. So LLMs are getting good at that?
They're getting there. There's been a lot of debate about whether LLMs truly understand theory of mind or if they're just mimicking it. But the fact that they can pass some of the tests is pretty impressive, and they're using these interacting LLMs to simulate social situations, like how norms emerge in a society.
That's fascinating. So what are some of the potential applications of all this?
The paper mentions medical diagnosis, logistics, and financial market analysis. But honestly, the possibilities are endless. Imagine AI assistants that can truly understand your needs and proactively help you, or AI agents that can collaborate to solve complex problems.
It sounds amazing, but also a little scary. What about the risks?
Definitely risks. The paper touches on the safety and security aspects. If LLMs are making decisions in the real world, we need to make sure they're not doing anything harmful or unethical. And there are questions about responsibility and liability. Who's to blame if an AI assistant makes a mistake?
Right? Like if a medical AI gives bad advice, who's responsible? The doctor? The AI developer? It's a legal and ethical minefield.
Exactly. But the potential benefits are so huge that we can't just ignore this technology. We need to figure out how to develop it responsibly and safely. The paper also mentions that agentic LLMs could help solve the training data problem.
The training data problem? What's that?
Well, LLMs need massive amounts of data to learn, but eventually we're going to run out of new data, or the data we have will become less useful. Agentic LLMs can generate their own training data by interacting with the world. It's like they're constantly learning and improving themselves.
So it's a virtuous cycle. Better LLMs lead to better agents, which generate more data, which leads to even better LLMs. That's pretty cool.
Yep. And that's why this field is so exciting. It's not just about building better language models. It's about building truly intelligent agents that can help us solve some of the world's biggest problems.
All right, let's dive into this research paper about how well LLMs fact-check information across different parts of the world. It seems like there's a real disparity here.
Yeah, it's not just about whether LLMs are good at fact-checking in general, but where they're good at it. The paper's title is Understanding Inequality of LLM Fact-Checking Over Geographic Regions with Agent and Retrieval Models, which pretty much sums it up.
Exactly. The researchers, Coelho, Mirza, Pupper, and McCoy, found that LLMs, even the big ones like GPT-4, Claude Sonnet, and LLaMA, do a much better job fact-checking statements from the global north compared to the global south.
So we're talking North America and Europe versus Africa, Latin America, and the Middle East, right? That's a pretty significant divide.
Precisely. They used a dataset of 600 fact-check statements, evenly split across those 6 regions, and tested the LLMs in 3 different scenarios. First, just giving the LLM the statement itself. Second, using an LLM-based agent with access to Wikipedia. And third, a best-case scenario where the LLM gets the official fact-check directly.
Okay, so that best-case scenario is like retrieval augmented generation, or where the model is given the exact document it needs. It's like giving the LLM the answer key.
Yep, RAG stands for Retrieval Augmented Generation. It's a way to improve the accuracy of LLMs by letting them pull information from external sources. In this case, they made sure the RAG system always retrieved the correct fact check. But even with that advantage, the regional gap persisted.
That's wild. So even when the LLM has the right information in front of it, it still struggles more with statements from the global south. What's the deal with the Wikipedia agent setup?
That's where things get even more interesting. The agent-based system, which is supposed to mimic how we might use LLMs in real life by letting them search for information, actually widened the gap. The researchers think this is because general knowledge bases like Wikipedia don't have enough region-specific nuances.
Ah, so Wikipedia might be biased towards information from the global north, or just not have enough detail about the global south. That makes sense. It's like the LLM is only as good as the data it can access.
Exactly. The paper highlights that these biases in computational systems can have serious implications, potentially making existing inequalities worse and misinforming certain populations. They stress the urgent need for better dataset balancing and more robust retrieval strategies.
So what are the key takeaways here? What did the researchers actually do and find?
Their major contributions are twofold. First, they quantitatively showed significant geographic disparities in fact-checking accuracy. Statements from the global south consistently underperformed. This highlights the need for culturally aware and geographically diverse model training and evaluation.
Got it. So more data from underrepresented regions is crucial. What's the second contribution?
Second, they explored whether adding external knowledge bases improves accuracy and reduces inequality. They looked at statement-only, RAG, and agent-based setups. The results showed that while RAG can be highly accurate when it retrieves the correct document, agent-based systems can actually make things worse, especially for the global south.
Okay, So RAG is great if you can guarantee the right information is retrieved. But a Wikipedia agent might introduce more noise and bias. It's like giving the LLM a library card, but the library is missing half the books.
Precisely. The paper also touches on related work like how LLMs can hallucinate facts and make reasoning errors, and the growing concern over digital misinformation. They also mention studies showing that ChatGPT can evaluate the credibility of news sources, but also tends to avoid binary answers in complex cases.
Right, LLMs aren't perfect. They can be wrong, biased, and sometimes just plain unsure. It's important to remember that they're tools, and like any tool, they need to be used carefully.
And the researchers used a specific methodology to reach these conclusions. They expanded on the global liar dataset, ensuring an equal number of true and false statements from each region. They also used a range of models, including GPT-4o, Claude Sonnet 3.5, and LLaMA 3.3, and ran them through those 3 fact-checking scenarios we discussed.
So a pretty rigorous setup. What did they find when they dug into the results?
The regional analysis is stark. The global north consistently outperformed the global south. North America often had the highest accuracy, while Africa, Latin America, and the Middle East lagged behind. They even used logistic regression to confirm these geographic disparities were statistically significant.
Logistic regression, for those who aren't familiar, is a statistical method used to predict the probability of a binary outcome, like correct or incorrect fact check, based on various factors like region and model. It helps them determine if the differences they're seeing are real or just due to chance.
Exactly. And the regression analysis confirmed that the global south was significantly underperforming compared to the global north. They also found that when the models were given the correct document directly, they all achieved very high accuracy, around 97 to 100%.
Which reinforces the idea that LLMs can be powerful fact-checking tools if they have access to reliable information. But the agent-based scenario is where things fell apart, right?
Big time. The agent-based scenario with Wikipedia access led to significant drops in accuracy. In some cases, GPT-4o and Sonnet 3.5 performed worse than random guessing. LLaMA 3.3 did better, but still had a noticeable decline, especially for claims from Africa.
That's a huge red flag. It suggests that simply giving an LLM access to a general knowledge base isn't enough. It needs to be able to find the right information and interpret it correctly. And that's where the regional biases seem to creep in.
And it's not just about being wrong. The researchers also noticed that the private models, GPT-4o and Sonnet 3.5, were more likely to answer unclear in the agent-based scenario. This hesitancy to make a definitive classification could decrease trust in LLM-based fact-checking systems.
So the LLMs are basically saying, I don't know, more often when dealing with information from the global south. That's not exactly confidence-inspiring.
Exactly. The paper concludes that these results highlight the strengths and weaknesses of current LLM-based fact-checking systems. They can be incredibly accurate in controlled environments with curated data, but they struggle with regional biases and the complexities of real-world information retrieval.
So what are the lessons learned here? What should we take away from this research?
The big one is that we need more diverse training data. The underrepresentation of the global south is a significant bias that needs to be addressed. It's not just about fairness, but also about building globally competent fact-checking tools.
And it's not enough to just throw more data at the problem. We need to think about the quality and relevance of that data. A biased knowledge base like Wikipedia can actually make things worse.
Right? The paper also points out some limitations. They focused on binary fact-checking and didn't explore how LLMs might be used to generate explanations or interact with humans. They also only looked at textual claims and didn't consider images or videos.
Fair enough. There's always more research to be done. But this paper provides a valuable starting point for understanding the regional inequalities in LLM fact-checking. It's a reminder that AI isn't neutral, and we need to be mindful of its potential biases.
Absolutely. As AI continues to influence information dissemination, we need to work towards developing systems that are equitable and effective across diverse global communities. It's about making sure that everyone has access to accurate information, regardless of where they live. Okay, let's dive into this research paper on using large language models, or LLMs, for mental health text analysis. The researchers compared 3 different strategies: fine-tuning, prompt engineering, and RAG, which stands for Retrieval Augmented Generation. They used the LLaMA 3 model to see which approach works best for things like emotion classification and detecting mental health conditions in text. It's a pretty hot topic right now, given the increasing need for mental health support and the potential of AI to help.
Definitely. And it's cool they're looking at different ways to deploy these LLMs. Fine-tuning, prompt engineering, and RAG all have their pros and cons. So what were the key findings? Which method came out on top?
So, fine-tuning was the accuracy champ, hitting 91% for emotion classification and 80% for mental health conditions. But, and this is a big but, it needs a ton of computational power and large training data sets. Prompt engineering and RAG were more flexible, but their accuracy was lower, in the 40-68% range. Basically, it's a trade-off between accuracy and resources.
That makes sense. Fine-tuning is like training a specialist, right? You're really tailoring the model to the specific task, but it takes time and effort. Prompt engineering and RAG are more like generalists. They can handle a variety of tasks with the right instructions and information, but they might not be as precise.
Exactly. And the paper highlights that. They used 2 datasets, one called Dare AI Emotion, which is a bunch of tweets labeled with emotions like joy, sadness, anger, etc., and another called S2MH, which is Reddit posts from the Suicide Watch and Mental Health collection, labeled with conditions like depression, anxiety, bipolar disorder, and suicidal ideation.
Okay, so a good mix of data to test on. What's interesting is that they used LLaMA 3, which is a pretty recent model. How did they actually implement these different strategies? Let's break down each one, starting with prompt engineering.
With prompt engineering, they tried both zero-shot and few-shot approaches. Zero-shot is where you give the model a task without any examples, like classify the emotion in this text as joy, sadness, anger, etc. That's it. Few-shot is where you give it a few examples to learn from before asking it to classify the text. They gave 2 examples for each emotion or condition to give it a balanced view.
Got it. So zero-shot is testing the model's inherent understanding, while few-shot is giving it a little nudge in the right direction. What about RAG? That one's been getting a lot of buzz lately.
RAG is cool. The idea is to give the LLM access to a knowledge base so it can pull in relevant information when it's making a prediction. In this case, they created a knowledge base from the training data itself. So when the model gets a new text to classify, it first retrieves similar examples from the training data and then uses those examples to help it make a decision. It's like giving the model a cheat sheet.
That's smart, especially for something as nuanced as mental health text. So it's not just relying on its pre-trained knowledge, but also on specific examples that are relevant to the task at hand. How did they build this knowledge base?
They used a technique called embedding generation to create vector representations of the training examples. Basically, they turned each text into a numerical vector that captures its meaning. Then, they stored these vectors in a vector database called ChromaDB. During retrieval, they embed the input query and find the most similar vectors in the database using cosine similarity. It's all about finding the most relevant context for the model to use.
Okay, so it's like a semantic search engine for mental health text? That sounds pretty powerful. And then, of course, there's fine-tuning. How did they tackle that, given the computational demands?
They used a technique called LoRa, which stands for low-rank adaptation. It's a way to fine-tune large models more efficiently by only training a small subset of the parameters. This significantly reduces the computational cost without sacrificing too much performance. They used a rank of 64 and an alpha scaling factor of 16 in their LoRa configuration.
Ah, LoRa. That's a clever way to get around the resource limitations. So they're essentially adding a small trainable module to the pre-trained LLaMA 3 model rather than retraining the entire thing. Makes sense. So, with all these methods tested, what were some of the more detailed findings? Did certain methods perform better on specific emotions or conditions?
Yeah, definitely. The fine-tuned model was a rock star across the board, but it did better with basic emotions like joy and sadness compared to more complex ones like love and surprise. Zero-shot prompting did surprisingly well for mental health condition detection, especially for depression and anxiety, but it struggled with nuanced emotions. RAG's performance was heavily dependent on the quality of the retrieved examples. And few-shot prompting actually underperformed compared to zero-shot, which was unexpected.
That is surprising about the few-shot prompting. Maybe the examples they chose weren't representative, or maybe they introduced some bias. It just goes to show that even with these advanced techniques, the quality of the data and the way you present it to the model really matters. What about the comparison to previous work? Did they beat existing methods?
They did. Compared to a previous study using relation networks, their fine-tuned LLaMA 3 model showed a significant improvement in classification accuracy and F1 score on the SWMH dataset. Even their zero-shot prompting approach outperformed the baseline, which suggests that LLMs can generalize to mental health-related text classification without needing specific feature engineering.
That's a strong argument for using LLMs in this domain. So what are the big takeaways from this research? What should people keep in mind when thinking about using LLMs for mental health text analysis?
The main takeaway is that fine-tuning can give you the best accuracy, but it's resource-intensive. Zero-shot prompting is a viable alternative if you can't afford to fine-tune, but you need to craft your prompts carefully. RAG can be helpful, but it's only as good as the information it retrieves. And few-shot prompting might not always be better than zero-shot. Ultimately, it's about finding the right balance between accuracy, resources, and deployment flexibility. Also, they point out that these models are better suited for initial assessment rather than definitive diagnosis.
Right? It's a tool to assist, not replace mental health professionals. What about the limitations of the study? What did the researchers themselves say could be improved?
They acknowledge that the computational cost of fine-tuning is a limitation. Also, the models were trained and evaluated on specific data sets, which might not fully capture the complexity of real-world psychological text data. They also didn't address the practical integration of these tools into clinical workflows, which would require collaboration with domain experts and rigorous validation. And of course, ethical considerations are paramount, especially when dealing with sensitive information like mental health data.
Absolutely. Bias, privacy, and the potential for misclassification are all serious concerns. It's crucial to have human oversight and to ensure that these tools are used responsibly and ethically. This was a great overview of the paper. Thanks for breaking it down.
All right, let's dive into this paper on polymer property prediction using multimodal machine learning. The title is Multimodal Machine Learning with Large Language Embedding Model for Polymer Property Prediction. Sounds like a mouthful, but the core idea is pretty cool.
Definitely. So they're using large language models, or LLMs, like LLaMA 3, combined with molecular structure information to predict how polymers will behave. Why is this approach interesting?
Well, predicting polymer properties is crucial for designing new materials. Traditionally, it's been a slow process involving lots of experiments. Machine learning can speed things up, but it needs good data and ways to represent polymers.
Right? And that's where the challenge lies, right? Polymers are complex, and we don't always have huge data sets to train our models on.
Exactly. This paper tackles that data scarcity problem by leveraging the knowledge already embedded in LLMs. These models have been trained on massive amounts of text, including scientific literature, so they've already picked up a lot about materials science.
So the LLM understands the language of polymers in a way. How do they actually use this knowledge?
They use the LLM, specifically LLaMA 3, to generate text embeddings from polymer smiles strings. Think of smiles as a kind of molecular code that describes the structure of a polymer. The LLM turns this code into a numerical representation, capturing the chemical information encoded in the string.
Okay, so the LLM provides a textual understanding of the polymer. But what about the actual 3D structure? That seems important too.
That's where the multimodal part comes in. They combine the LLM embeddings with structural embeddings from a model called Unimol. Unimol is trained on millions of 3D molecular structures and is great at capturing the geometry and shape of molecules.
Ah, so it's like having both a textual description and a 3D blueprint of the polymer. How do they combine these two types of information?
They created a model called PolyLLMem, which fuses the LLM and Unimol embeddings. They use something called low-rank adaptation, or LoRa, to fine-tune the embeddings based on their limited polymer dataset. This helps to make the embeddings more relevant for the specific polymer properties they're trying to predict.
LoRa? So it's like a targeted adjustment to make the model more sensitive to the nuances of polymer chemistry?
Precisely. And the cool thing is, PolyLLMem performs comparably to, and sometimes even better than, other models that require pre-training on millions of polymer samples. This shows that LLMs can effectively capture chemical information from polymer smiles, and that combining textual and structural information is a powerful way to overcome data scarcity.
That's a big deal. So what kind of polymer properties were they predicting?
They looked at 22 different properties, including things like glass transition temperature, Tg, melting temperature, Tm, thermal decomposition temperature, Td, density, band gap, refractive index, and even gas permeability.
Glass transition temperature. That's the temperature at which a polymer transitions from a hard, glassy state to a more rubbery state, right?
Exactly. It's a key property for many applications. They also looked at mechanical properties like Young's modulus and tensile strength, which tell you how stiff and strong the polymer is.
And how did they collect their data? Did they synthesize a bunch of new polymers?
No, they compiled a data set of nearly 30,000 data points from existing literature and databases. This included both experimental measurements and data from DFT calculations, which are computational methods for simulating the electronic structure of materials.
Okay, so they're leveraging existing knowledge rather than generating new data. That makes sense given the focus on data scarcity. What's P-Smiles, by the way? They mention it a lot.
Good question. P-Smiles stands for polymer smiles. It's an extension of the standard smiles notation that's used for small molecules. P-Smiles allows you to describe the repeating units, end groups, and connectivity patterns in a polymer chain.
So it's a way to represent the entire polymer structure in a compact text-based format. Makes sense why they'd use it with an LLM. How did they train the model?
They used 5-fold cross-validation to ensure a robust evaluation. This means they split the data into 5 parts, trained the model on 4 parts, and tested it on the remaining part. They repeated this process 5 times, each time using a different part for testing. They also used a learning rate scheduler and early stopping to prevent overfitting.
Overfitting? That's when the model learns the training data too well and doesn't generalize well to new data, right?
Spot on. They also compared PolyLLM to a bunch of baseline models, including random forests, linear regression, and support vector regression, using both molecular descriptors and Morgan fingerprints as input features.
Morgan fingerprints. Those are another way to represent molecular structures, right? They capture the presence of different substructures in the molecule?
Yep. They're a common choice in cheminformatics. The results showed that PolyLLMem generally outperformed the baseline models, especially for properties like density, glass transition temperature, and band gap.
That's impressive. So the combination of LLM and structural embeddings really pays off. Did they try to understand why the model was making certain predictions?
They did. They used a technique called integrated gradients to analyze which parts of the P-Smiles string were most important for predicting the glass transition temperature. They found that the model focused on key chemical motifs and structural features that are known to influence Tg in real polymers.
That's great. It's not just a black box. They can actually see what the model is thinking. So what are the limitations of this approach?
They acknowledged that PolyLLMem struggled to accurately predict certain mechanical properties and gas permeability. This suggests that further model refinement or additional data may be needed to improve performance in these areas. Also, while it performs well, it doesn't always beat more specialized models for certain tasks.
Okay, so there's still room for improvement. What's next for this research?
They suggest enhancing the embedding model by leveraging token-level embeddings and multi-head attention mechanisms. This could potentially improve the accuracy of polymer property predictions even further. Basically, digging deeper into the LLM's understanding of the polymer language.
Sounds promising. Overall, it seems like a really clever way to tackle the data scarcity problem in polymer property prediction by combining the power of large language models with structural information. Definitely a step in the right direction for accelerating materials discovery.
So we're diving into this paper about code switching in NLP. Code switching, for those who don't know, is when people mix languages in the same conversation. Think of it like sprinkling Spanish into your English sentences, or vice versa.
Exactly. And this paper looks at how we can use synthetic data, basically AI-generated examples, to help language models get better at understanding code switching. The big question is, does the quality of this fake data actually matter?
That's the core of it. They're tackling a major problem. We don't have a real-world code switch data to train these models effectively. So data augmentation, creating more data, becomes crucial.
Right? They're building on previous research, but they're going further by testing different augmentation techniques across multiple NLP tasks. They looked at machine translation MT, automatic speech recognition, ASR, and even cascaded speech translation, ST.
Okay, so MT is translating text, ASR is turning speech into text, and ST is doing both at once, speech to text to another language. Got it. What kind of augmentation techniques did they use?
They used a bunch. First, lexical replacements, which is swapping words with their translations. They did this randomly, but also using a model to predict where code switches are likely to occur.
So instead of just randomly replacing words, they tried to be smart about it using a predictive model. Makes sense. What else?
Then they used linguistic theories, specifically equivalence constraint EC and matrix language frame MLF. These are frameworks that describe how code switching tends to happen grammatically.
So trying to make the AI-generated code switching sound more natural and grammatically correct. And finally, they used back translation, which is translating from one language to another and back again to create variations.
Precisely. They trained a model to translate English into code-switched Arabic English. So they'd translate an English sentence into this mixed language, creating a new code-switched sentence.
Okay, so they've got a whole arsenal of techniques. What were the key findings? Did the quality of the synthetic data actually matter?
Here's where it gets interesting. It depends on the task. For machine translation, the quality of the synthetic data was really important. If the generated sentences were more natural, the MT models performed better.
That makes intuitive sense. Garbage in, garbage out, right? But what about speech recognition?
That's where the surprise is. For ASR, the correlation between data quality and performance wasn't there. Even if the generated sentences sounded weird to humans, they could still improve the ASR model.
Whoa! So even unnatural code switching could help the ASR model. Why do you think that is?
They suggest a few reasons. One is task complexity. ASR models might struggle more with code switching in general, so even imperfect synthetic data can provide a boost. Also, data diversity might be more important for ASR than perfect naturalness.
So the ASR model is just happy to see any code switching, even if it's a bit clunky. It's like, hey, I'm learning something new.
Exactly. They also looked at perplexity, which is a measure of how well a language model predicts a sentence. They found that perplexity didn't always align with human judgments of naturalness.
So a model might think a sentence is perfectly fine, even if a human would cringe. That highlights the need for human evaluation, even if it's time-consuming.
Definitely. The paper concludes that back translation and predictive-based lexical replacements were consistently good across tasks. But the importance of quality really depends on the specific NLP task you're tackling.
That's a really valuable insight. It means we can't just blindly generate data and hope for the best. We need to think carefully about the task and what kind of data will actually help.
And they point out that this study focused on Arabic-English code switching. It would be great to see if these findings hold true for other language pairs as well.
Absolutely. And they mentioned that using large language models, LLMs, for code switching generation is a promising area for future research. It'll be interesting to see how LLMs can improve both the quality and diversity of synthetic code switch data. Wow, what a journey! We covered so much ground today, from AI agents that can reason and act in the real world to the surprising regional biases in how well AI fact-checks information. It's clear that while the potential of this technology is immense, we're still grappling with some fundamental challenges.
Absolutely. That deep dive into agentic LLMs really highlighted how AI is moving beyond just generating text. The idea of AI assistants that can proactively help us, or AI agents collaborating to solve complex problems, is incredibly exciting. But we also can't ignore the ethical and safety considerations.
And the fact-checking study was a real eye-opener. It's a stark reminder that AI isn't neutral, and we need to be incredibly mindful of the biases that can creep into these systems, especially when it comes to representing different parts of the world.
Then we explored how different AI techniques can be used for mental health text analysis, and how fine-tuning can give you the best accuracy, but it's resource-intensive. It's all about finding the right balance between accuracy, resources, and ethical considerations.
And who could forget the polymer property prediction? Combining large language models with structural information seems like a game changer for accelerating materials discovery, especially when data is scarce.
Finally, the code switching paper was fascinating. The fact that the quality of synthetic data matters so much for machine translation, but less so for speech recognition, was a real surprise. It just goes to show that we need to tailor our data augmentation strategies to the specific task at hand.
It's amazing how quickly this field is evolving. Each of these research areas is pushing the boundaries of what's possible with AI, but also raising important questions about fairness, responsibility, and the future of work.
Definitely. And it's a conversation we need to keep having. Thanks for joining us on this deep dive. We hope you found it as insightful as we did, and we can't wait to explore more of these topics with you in the future.